Okay, hello everybody, this is Brian O'Neill, and I'm going to talk through problem 10.1. So 10.1a says determine principal stresses of sigma ij is equal to this stress tensor right here. First things first, we have to find our eigenvalues. So using the determinant of the first part of equation 10.1, so we're taking the determinant of that, we can then solve for lambda, which is our eigenvalue. So first we set it equal to 0, and then we go in and we get the determinant of this right here. So it'd be this times this minus that. No. This times, oh, well, I just wrote it out here. How about that? Times negative lambda times 1 minus lambda minus 4, close bracket, minus negative 2 times negative 2 plus 2 lambda. And if we expand that out a little bit, we get this equation here. Uh, Doing another step, by multiplying this times that times that times that times that times that, etc. We can then get this long string here. You can see where I scratched off some terms we're canceling. Eventually you get negative 3 lambda squared. I just said that wrong. Eventually you get negative lambda cubed plus 9 lambda plus 0. Um, to make this simpler on myself, I took out a lambda from there because I didn't know how to solve this, but I do know how to solve this. So we took the lambda out, and then you see lambda squared minus 9. I took a negative sign out too. It's just more obvious. And so this is a common equation right there where you got the roots of x squared minus 9, it'd be x plus 3, x minus 3. This time it's just lambda plus 3, lambda minus 3. And so you see our roots here is, you could think of this as lambda minus 0 times, yeah, times all that. So this first one's 0, this second one's negative 3, this last one's 3, because you want it to equal 0. And so we solve for our eigenvalues, which I've written out right here as a vector for reasons unknown. Okay, now that we got our eigenvalues, we can go find our eigenvectors by plugging them back in. So I wrote out equation 10.1. This is first part of it. This is the n vector, and it's a little hard to see because my camera's not doing too well today. But I just, instead of writing e's and all that, I just wrote n sub x, n sub y, n sub z. Just to make it simpler on myself, it's probably a confusing notation for everybody else, but regardless. So once we take these and make equations out of this matrix, we get these three equations right here. Solving these three equations, we eventually get the relationships nz equals negative 2ny, nz is equal to nx, and nx is equal to negative 2 ny. I picked up a fancy trick back in chapter 7 after watching the video. We set n equal to 1. So if n is 1, then ny must be 1, negative 1 half. And then nz, since nz is equal to nx, must also be 1. Now we get the non-unit eigenvector, but I want to make it a unit vector, so I normalize it. So I take the vector we just got, 1, negative 1 half, 1, and I divide it by its magnitude. So its magnitude happens to be 1.5. Taking all those values, dividing them by 1.5, you get 2/3, negative 1/3, and 2/3 again. And that is our first eigenvector. Next, we plug in our following eigenvalue. This one's going to be 3. And we do the same thing again. You can pause the video if you want to see what I did. But effectively, I just did the exact same process. We get our three equations. We find the relationships, and I set n equal to 1. Then when I have my non-unit vector eigenvector, I normalize it with the magnitude of n again. Doing that, we find that the magnitude of n is 3. So we put all those values over 3 and we get 1/3, negative 2/3, and negative 2/3 again for our second eigenvector. For our final eigenvector, we set lambda equals to, did I do positive 3 twice? Hold on here. Ah, okay, yeah, this should be negative 3. lambda equals -3. I confused myself because it was sigma minus a negative, so it became +3. Anyway, repeating the process one more time, we eventually get down to our non-unit eigenvector, which is 1, 1, and -0.5. And then we divide it again by our magnitude, which is once again 1.5. Ooh, camera's having a hard time with this. And so our final eigenvector, which it might be hard to see here, I don't know why my camera's doing that, but it is 2/3, 2/3, and -1/3. Thank you very much.